We have successfully verified the physical data path from the QEMU xHCI controller into the input server. This was achieved in a pure no-stat environment, executing without a C standard library or standard Rust utilities. The input loop evaluates hardware state through polling, which eliminates thread context switches. The memory for this process is isolated by Intel memory protection keys. Every protection domain is separated at the hardware level. The architecture permits no direct memory sharing across domains. Input is a bifurcated data flow, raw hardware voltage before decoding into semantic events. The SexUSB server at Layer 2 manages this hardware polling without UI awareness. Data then flows to Layer 4's Sex input, normalizing raw bits into standardized coordinates and button presses. The frame buffer remains a separate domain, governed by the Sex display compositor. This separation ensures that a hardware timeout or failure inside the USB driver cannot corrupt the compositor's memory state. To initialize the bus, we interface directly with the QEMU bare metal xHCI controller. The kernel maps the bar 0 memory window, providing access to probe the capability registers. We allocate the command and event rings using static memory blocks. No dynamic heap is used during this boot phase. The controller uses 64-bit control registers, which are written in two 32-bit halves. The xHCI specification suggests writing the upper half first. In QEMU, this causes the internal pointer to latch to the uninitialized lower half, which evaluates to 0. The emulation logic locks the pointer before the lower bits submit, breaking the command ring. We resolve this by inverting the sequence. Writing the lower D word at offset 0x18 first, then the upper D word at 0x1c latches the fully initialized pointer. This write order is applied to the command ring control register and device context base address. Correcting these hardware states allows us to stabilize the environment without relying on external driver translations. With the pointer stabilized, we execute a bounded sequence to stop, reset, and run the controller. Assigning an address to the virtual device initially triggered a transfer request block error. The issue was in the TRB layout. The hardware uses a shared 6-bit type field for both commands and data transfers, but their numerical values overlap. We submitted an address device command, type 11. Because of the overlap in the shared field, the controller interpreted that integer as a no-op transfer. We corrected the constants and moved to descriptor fetching, starting with an 8-byte read on endpoint 0. We expand to the full 18-byte fetch. Zeroing the buffer beforehand ensures a short read doesn't leave stale data masquerading as hardware state. We map connection speed to determine our limits. A speed ID of 3 indicates super speed, requiring a max packet size of exactly 512 bytes. Strict structural typing and bounded limits provide a robust defense against silent corruption within the hardware. We move forward with a 2-phase walk through the configuration descriptor to locate the HID endpoint. Interface class must be 0x03, subclass must be 0x01, and protocol must be 0x02. We set the configuration, maintaining specific bitwise invariants during the setup packet submission. We require the interrupt on completion bit to be placed at double word 3, bit 5. For QEMU compatibility on control transfers with no data stage, we set the direction bit to in at double word 3, bit 6. We then transmit a set idle command. This forces the virtual mouse to emit continuous reports even when stationary. Endpoint 1 is mapped as an interrupt in transfer ring. We pull the ring boundary for incoming bytes rather than using a standard interrupt handler. When a 4-byte packet arrives, we unpack the raw bytes locally. Byte 0 maps to button states, byte 1 to the x-axis, byte 2 to the y-axis, and byte 3 to the scroll wheel. This translation uses bitwise integer math, requiring 0 heap allocations to process the input frame. Forcing periodic reporting and direct state polling avoids the complexity of asynchronous threading context. The final requirement is moving these decoded integers out of the SexUSB domain. During boot, the kernel granted a single capability route between these two servers. SexUSB executes a protection domain exchange call, pushing the packed arguments through slot 9. The Sex input server confirms receipt, validating the pipeline from hardware to the input server. This transfer was achieved without passing a raw memory address across the protection boundary. The next engineering objective is Layer 5, semantic translation. SexInput will convert these raw integers into normalized pointer events. It will route events to Silk-Shell to calculate focus, which then commands SexDisplay to update the cursor hardware plane. This lock-free, capability-routed hardware pipeline demonstrates that real-time UI interaction is achievable within a SASOS architecture.